Okay, so this is the last topic, and what it is really is a very quick look under the hood at Simulink. Now, as I said quite a few weeks back, is that MATLAB and Simulink are kind of black boxes, and they mysteriously throw out answers, which is great. But, you know, in life it's always good not to rely on black boxes if you don't know how they work, because someday they might let you down. So it's no harm to have some idea as to what's going on under the hood. So, how it works is really grounded in numerical analysis, which is stuff that you guys have done a lot more recently than I've done, as in probably second year maths here. Actually, I see you guys have probably done this here, I suspect. Or are you doing numerical analysis?
No, I don't. No.
So do you do differential equations, have to solve them with a biro?
Yeah.
Iterative approaches, yeah?
No.
Ordinary differential equations?
We did it first year, like maybe in semester 1, but we haven't done it since then.
Alright. Okay, well, this lecture should make a little bit more sense. Kevin, you're probably an expert at all this. So he can give a lecture whenever you get stuck. Alright, so as you know, or maybe you don't know, Simulink works through the use of solvers. I haven't really touched on it because we've done it run as a black box. But so what it does is when you have a model, right? Very simple model here. You have a sine wave and you multiply it and you add a bias to it. So when you have a model like that and you press run, Simulink decides, right, what do I do next? Well, it knows the runtime usually, which is by default 10 seconds in this one. And it says, right, how do I do this? And it looks at the different types of blocks. And it goes through an initialization phase. And for a simple block like this, or a simple model like this, there's not a lot to be done, except obviously it looks at the parameters of the sine wave that you've set. It looks at the parameters of the gain block, the bias block. And it says, right, okay, I can see what I need to set the sine wave. It has an amplitude of 1 and a period of whatever. So it initializes, but then it also looks to see, right, is there anything here that dictates that the order of the block should not be just left to right, because obviously the arrows are going left to right. And in this case, there are no states. So it just goes right through. So the general process is it initializes, and as we see today, that one of the most important things it does is it determines the block order, and then it enters the simulation loop. So it knows the runtime, so it says, right, the person who designed this model wants me to run it for X time units. Okay, so X time units might be 10 seconds, it might be a week if you're looking at temperature data, or it could be a month, or it could be a year, or it could be a decade. Or if you're looking at global warming, it could be a century. And it says, right, this is the timeline I've been given to run the model. The question is, how often will I run the model? Because obviously there are an infinite number of time steps, potentially, between start and finish. I do have another marker somewhere. I can see it. Yeah. Okay. So this is the start, this is the finish, so it decides how many iterations will I have. What size will each step be? And Simulink works that out as it's going along, usually. It depends on the way we set it up, as you'll see. So at each time step, so these are certain time steps here. At each time step, it calculates the block outputs and the state. So you have a sequence of blocks here, and they have outputs, as you can see. So each step it does that. It then checks for discontinuities. So what I mean by that is, and we've kind of touched upon this a few weeks ago, it looks to see, right, are things changing rapidly here? Has there been a sudden change in direction? Have we crossed the 0 axis? And if it detects those sort of things, it says, right, maybe I need to be a little bit more careful. Because a lot of the time when you approach 0, things can start to increase again. So it looks for those kind of out of the norm events, and if it finds them, it might decide to reduce the step size so that essentially So in other words, let's say the parameter is going like that, and MATLAB is running, or Simulink is running fixed steps. So it might run it here, and it might run it here. If the step size is this, so let's say that's a fixed step size. They're supposed to be fixed steps. So it runs here, it runs there, it runs there, runs there, there, and then it jumps across to there. So in other words, you might skip, it might miss this bit here. So instead of that, it will run multiple times around here, so you actually do catch the full parameter and its state. And based on these discontinuities, it determines the next simulation time. So generally, these solvers can be defined as either fixed step or variable step. They can also be used in discrete and continuous systems. Now, the systems we've been seeing so far are, in Simulink, are largely continuous systems, but the simpler ones aren't. And of course, what Simulink does as a black box is it tries to approximate stuff, and it introduces errors in doing so. So you just need to be aware that as a black box, it has its limitations, and in order to control the error, you need to kind of know what's going on and maybe make changes. I'm going to show you what that means as we go through this. All right. Well, a very simple model. So we have a sine wave, put it through a gain block of 5. So there's our input in A. A gain block of 5, so in rate. And then finally we have a bias of 3. Right? So this model runs for, as I said, 10 time units. So if you look at display here and you click on that, you'll see it allows you to look at the block sorted order. So in other words, you're asking Simulink, in what order did you calculate, did you run through your model? And because there's no state, so there's no memory here. You have an input and you have an output for each step. So at each step, you don't have to remember what the previous stage was. So you can see Simulink is telling you here that the order is 1, 0, 1, 2, 3. So in other words, you're going from left to right. Okay? And that's a useful thing maybe to have a look at when you build your models. So display and then sorted order. Now, this is the same model, but I'm just showing you some stuff here. So when you run this model, you get your Y out and your T out. And of course, T out tells you how many points from start to finish, how many steps did MATLAB or did Simulink take. And as you can see, there are 51 data points in the output file. So how many steps did it take? 50, right? It's like a ladder. So there are 50 steps. So if you want to look at, well, how often and what were the step sizes, you can use that's very easy to work it out. So you just look at T out, you're looking at the difference between respective T out values, and then you're plotting them. So it's a nice way to just very quickly see what the step size was. And as you can see here, but you can see it in any event, I've shown it to you here, if you look at the T out vector, this is what you see. So as you can see, the step size is what? 0.2. And it's fixed. It goes right through from start to finish. So in other words, we have a fixed step size here. Okay, here's a similar model. The only difference being is I've replaced the sine wave here with the pulse. And again, it's much the same stuff. You've got a gain of 5, you've got a bias. So we've got our pulse in purple. We've got our gain, multiplying it by 5 in blue, and then we add in red, we add the bias. So again, when you look at the block order, it's the same. There are no states here. And similarly, when you look at the step size, it's the same. Okay, 0.2. By the way, if you decide to run that, and you should, be careful of the y-axis here. Because I had to go in and manually set the y-axis to have a minimum of 0 and a maximum of 0.5. By default, when it sees all these 0.2s, it'll set the minimum of 0.1999999 and the maximum of 2.00001. And you'll see a kind of maybe some small changes here, but in fact it's just because of it's just essentially it's rounding errors is what you're looking at. So just be careful about that when you do that. Okay, so the same idea here. The output vectors are the same size, 51. Okay, now let's look at something a little bit more complicated. So what do we know about integrators at this stage in MATLAB? In Simulink, what's one of the parameters you set? The initial value. So in other words, now when you decide to press run here, Simulink has a look and it says, right, we have a pulse generator, we have an integrator, we have a bias, and we have an output. So it's literally the same except for this bit here. But it says, yeah, an integrator has to have an initial value. So the first thing I do when I run this model is I check the integrator initial value. So when you look at the sorted order, lo and behold, this is the first one. So 0, 1, 2, and then it goes back in to take the next input. So again, it's just showing you, hopefully, maybe a bit more, maybe even for you, David, you're saying you're struggling a bit with Simulink. This might help to actually understand how it actually goes about its business. Okay, so if you do the same thing here now, so what I'm saying is, it's also running for 10 time units, same as before here. And you can see the output here. Right? So when we look at the step size, what do you see here? So generally speaking, it's 0.2, but you can see it ramps up here, and then we get a dip here as well. And this is the output time. And these are the steps, of course. So as you can see, by default, a lot of the steps are 2. Steps are 0.2, 0.2, 0.2. But here we get a change. So because you've got an integrator and a pulse generator, Simulink says, right, hold on a minute here, we're getting these very sudden changes. Let's have a look at them more closely. And that's why you get this dip. And that's why you get this, at the start as well, you get the variable steps. And obviously here we have the, what you'd expect. Here's your pulse, there's the integrate of the pulse, and that's just the bias added on. Okay? So again, this is what's running in the background every time we press run. Now, as you know, in this version of Simulink, you can actually iterate through a model. So maybe that's something you could do as well to see how this happens from step 1 up to, there are 55 steps here, right? Because we take a couple of extra ones at the start and at this point here. Okay, so last week we looked at how you can, and your assignment for this week is taking a model and creating subsystems and then creating masks. And as you know, one thing about a mask is it allows you to set parameters, like the initial condition for an integrator. So when you click on this mask, this is what you get here. And of course, when you click on this, it brings up this dialog box. What is the initial condition? One thing to be aware of, when you introduce masks into your models, and you ask Simulink for the blocked order, or the block order, it actually changes a bit, but we won't go into that level of detail. So as you can see here, in this model here, when you look for the sorted order, it goes 0, 0, 0, 1, 0, 2. But we're not going to consider why that is, because I think it'll only confuse things a bit. But just in case you come across that, you might wonder why that is. But ultimately, just stick with kind of understanding it in these more simple models. Okay. Same one again, except I've got rid of the pulse and I've put in a sine wave. So we see here, there's the sine wave here. Not very clearly shown because of the step size. The integral of it, and then you're adding on a bias. And as you can see, again, we're running for 10 time units, and there is the T output. So as you can see, we have a fixed step size of 0.2 as well, which you can see there. So the value of T out is 51. Okay. So at this stage, when we were looking at setting up our models, we've used the configuration parameters. So you're familiar with this dialog box here when you'd be setting your data import and export. But hopefully at this stage we've had a look at this dialog box as well, which tells you essentially what MATLAB and what Simulink are doing behind the scenes. So how is it solving your model? So you can see here you have a start time, you have a stop time. Here you have your options for your solver. So you have variable step or you have fixed step. And then you have different types of solvers in terms of differential equations, particularly for continuous systems.
You said we should be familiar with this. We haven't seen that before.
Well, you've seen that dialog box before.
No.
No.
But when you're setting the data import and export.
No.
Never seen that.
Never seen it before.
Okay. I think of your labs. Anytime you're reading data input into a model.
No, actually, let's read.
Yeah.
That's what we've been using scripts, and that's it. I've never seen that.
Lab 6. Let's think about lab 6.
Do we know this for lab 6?
Yes.
Is this why we all can't do lab 6 then?
I didn't use this today. I don't think it's
Okay, I'll have to go back and look at lab 6. Anyways, this is, if you look under, this is essentially looking under the hood of the solver, okay?
Yeah.
So you can see here, it tells you here, and you can set parameters here, whether it's variable step or fixed step, alright? And we're going to look at some of these options here today. Okay, so fixed or variable step, and then continuous or discrete. Now, a general rule of thumb, if you have an integrator in your model, you need to use continuous solvers. But as you can see here, you have variable step and fixed step, and that's a very simple approach. It's either, is the step size constant, or is it variable? Are you going to let Simulink decide itself whether the step size is going to change as the parameters change, or are you setting a fixed step for each as you go from start to finish? And in terms of continuous and discrete, this is just a very simple model, and I'm not sure that I put some models up on Blackboard last night. No, not this one. Maybe I'll put this one up as well, because it's a nice indication of the difference between the two. So we have two sine wave blocks here, except one of them is continuous and one of them is discrete. And here I'm setting the sample time of 0.5. So your step size is 0.5 for that block. And here, because it's a continuous system, the sample size or sample time is set to 0. So in other words, it's variable. And you can see it here in the output, that the red one here, discrete one, is jumping up in blocks. So, I mean, the engineers, the few of them that are here, are probably more familiar with discrete and continuous systems. Have you done any digital signal processing? Engineers? Okay. Have you covered discrete systems and continuous systems and control systems? Now, I know the IT guys haven't done this, so. But as you can see, it's a fairly, I think, easy to understand concept, discrete systems versus continuous systems. So really, depending on what Simulink is trying to solve, you need to be aware of whether it's a discrete or a continuous system. Okay, Now this is where your maths maybe in last year. Does ODE 45, does that ring any bells with anyone? No? With you, Kevin, yeah? Yeah, okay. What about anyone else?
Heaven, get out.
Well, I mean, this is just behind the hood stuff. I'm not going to be asking you questions in the exam about what is ODE 45, right?
Okay.
But did you not cover the numerical analysis? Okay. Engineers? Right, okay. I did it, but that was the last millennium, alright? So maybe they've upgraded the syllabus since. Okay, or syllabi. Alright. Okay. So if you look at these two sine waves and you double click on them, they're both, this is the parameters for both. The only difference being here, everything else is identical except for here. For a continuous system, the sample time is 0, and for a discrete system here, by default, it's set to 0.5. And that's why when you drag this block across, you get these steps in 0.5. Alright? Okay, so in summary, sample time 0 means it's a continuous block. Sample time greater than 0 means it's a discrete block, like in our case it's 0.5. And you may have seen this already in some of the blocks. You see sample time minus 1. And that just means the sample time is inherited from the other blocks in the system. So it's just really an understanding of when Simulink is running, how often is it going to run? What is the step size as you run through from start to finish? So whether you use a fixed step or a variable step solver really depends on a number of things. The first one is what level of accuracy are you looking for? So remember I said here that if you have a fixed step, Simulink might jump from this side over to that side, in which case it'll forget about the bit in the middle. So in terms of a mathematical approximation, it might introduce a large error here. So in other words, what Simulink works on essentially is something like this, right? Rather than something that's a lot more granular in terms of here particularly. And really, there's two things you look at. One is, how accurate do you want to be? Because the more accurate you want to be in terms of step sizes, the slower the model will be. Because it has to run at all these iterations. Remember, at the end of the day, it's just a computer that has to run an iteration so often. So it's like a for loop. It runs through so many times. If you reduce the number of iterations, needless to say, the model will run more quickly. If you have a much larger loop iterations, it obviously takes longer to run. So it's a question of accuracy and speed. So if you have a fixed step model, so in other words it runs at fixed intervals, you can indeed miss these change points. And as a result, you don't control the integration errors. So in other words, you're saying, to hell with it, I don't care what size of an error there might be, I just want to run the model at every so many time units. And obviously you don't detect discontinuities either. On the positive side, it's suited to real-time code generation. Now intuitively, why do you think a fixed step size suits real-time code generation? It's a bit like a loop. You know, in a for loop or a while loop, you're iterating, your step size is fixed. You know, so for I equals 1 to 50, I++ in C or Java. So you have a step size of 1 in that case. So it's more similar to what you'd see in a normal piece of code in terms of the step size is constant. And indeed, one thing we don't do in this course is, if you develop a Simulink model, you can actually take your model and you can generate Java code from it. So essentially it will just output the full Java code for your model. But of course, your step size needs to be fixed. So in other words, you can just create a for loop where you have this type of a fixed step solver. If you have a variable step solver, of course, it will decide, hold on a minute, things are changing rapidly here. I need to take a closer look at this point and therefore it will run a number of iterations around here so that it does capture the full profile of the parameter. So as a result, variable step solvers will control the error and they will detect these events. So you might say, why not always use variable step? Well, of course, the problem is it can be slower. Usually, not always, but can be slower. It depends on the type of model, but of course, it is more accurate. So when the variable is changing slowly, it will increase the step size. It will say, not much is going on here. I can afford to increase the step size. But when things are changing rapidly, or it sees a sudden change, it might say, I need to reduce my step size just to make sure I don't miss something. So it's all logic that's built in behind Simulink. But again, you need to be a little bit aware of how it continuous state solvers. And as you know, at this stage, the step sizes vary to control the error as the simulation progresses. So in other words, the step size will change as you go through from start to finish. And when you're using a variable step solver, you actually decide what you're happy with in terms of the error. So you can, MATLAB or Simulink will set up default values, but if you want, you can change them to control that error yourself. So it depends on really how much accuracy you're looking for. So for example, if you look at this dialog box that you've never seen before, and you see here, this is a variable step solver, and the exact solver it's using is ODE45. So Kevin, since no one else covers these things, do you actually go through the different types of solvers in your course?
Yeah, I took a course.
Sorry?
I took a course just
Yeah, yeah. So, in other words, let's say you're looking at a curve like this, and I suppose the easiest way maybe of explaining it would be, you know, we do curve fitting, and here we have a set of data points. Right. And we decided, right, give me a third order approximation of that. And MATLAB might give us something like that. And then you said, right, give me a fifth order approximation of that. And MATLAB will do something like this. In other words, the fifth order one is more precise. Okay? So we've seen this already. So if you look at ODE45, what it's actually doing is it's working through the simulation using both fourth order and fifth order. Okay. So here, ODE45 evaluates the integral using the fourth order and the fifth order, and it looks at the difference between the answer. It says, right, I've done this with fourth order, I've done this with fifth order, and the result I'm getting is x and y. I look at the difference between them and I say, right, that's the magnitude of the difference between 4 and 5. Is that acceptable? So if it's a very large error or difference, it says, you know what, maybe I need to go back and shorten my step size and run it again. So when you're using a continuous solver, such as ODE45, this is all going on in the background over that timeline of 10 execution units. So by default, Simulink has these error bounds, and it will run the model using those error bounds. And it has two error bounds it looks at. It looks at the absolute error, and it looks at the relative error. Now maybe rather than trying to explain that, it might be easier to explain it here. So here we have a model, and you can see the time on the x-axis here. And there's some block in it with a certain state. And that state is changing, as you can see, as you go through the model. And remember, with Simulink, this is a real system, whatever it might be, and you're trying to model it. Okay? And of course, as you run through the model, you might have some errors in terms of approximations. And you specify, or MATLAB and Simulink specify two types of error. There's a relative error and there's an absolute error. So up here, where the state size is quite large, and let's say when I say a relative tolerance, so you might say, I'm going to set an error margin of 1,000th of the state value. So the relative tolerance might be 1,000th of what the state is. So when the state is fairly high and fairly large, obviously the 1,000th of that will be relatively large. However, when the state value is very small, 1,000th of it will be tiny. So in other words, if that's, if you have a very large state, 1,000th of it could be a certain amount here. But when you have a very small state, 1,000th of that is minuscule. So you specify an absolute tolerance and you specify a relative tolerance. And Simulink works between those bounds. So you see here, so again, variable step, ODE 45. So by default, these values are set. So the relative tolerance is 1,000th of the state value. And the absolute tolerance is decided by Simulink itself. So again, it's back to the black box. It decides itself what is an appropriate absolute tolerance for this model. And then as it's running through the iterations, in this case it runs through using 4th order and 5th order and looks at the difference between them. And it compares that difference to the relative tolerance and it compares it to the absolute tolerance. And if the error satisfies either of those, it proceeds. So it says, right, we're okay, we're within the error bounds for Simulink, we can go on to the next step. If, however, it detects a larger error than the tolerances, then it says, no, error is too big, reduce the step size, go back in here and have another look. So that's why, as you run through your model, the step size can change, because at each step it does this, and then it decides to either go on or to go back and go through it again. Okay. And that's why for these discontinuities, the variable solvers will adapt by taking additional time steps to give you better accuracy. So just to show you how that works in real life, let's look at a number of examples. Actually, no, sorry, this is just, well, as I said, if you look at the variable step solvers, see this dialog box here, there's a whole lot of different solvers you can use. A lot of the time ODE 45 is chosen, but you can select other ones. So you can select, for example, where do I have it? Here. Yeah. A whole lot of different solvers. You do stiff solvers as well, Kevin? Okay. So this is just showing you the error. So if you use ODE 1, it's telling you here what the error might be. Okay, so a quite significant error here. If you use ODE 45, as I said, it looks at this error here, and it says, right, the absolute error margin is this, the relative margin is that. Is at least one error less than its tolerance? Yes. Go on. No. Go back. Okay, so let's look at an example. So here's our model, our pulse generator, our integrator, and our bias. So needless to say, you run through, here's your pulse, that's the integral of it in blue, and then you add 3 to it, and you get your final output there in red. Okay? Now what I'm specifying here, so when you go to configuration parameters and look at the solver, I'm specifying a fixed step solver. Alright? And I'm setting the fixed step size, so I'm saying, right, I want a fixed step size, but let Simulink choose the actual size of the step. So I set that to auto, which means Simulink will say, right, it's up to me to decide what step size will be as we run through this model. So we're running for 10 time units. Here's our pulse. So the pulse has an amplitude of 1, a period of 1, and a pulse width of 50%. So as you can see, an amplitude of 1, a period of 1, and it's on for 50% of the time. So when you run that model, and of course Simulink decides what the step size would be, what is the step size?
Half. Half.
A half, right? So Simulink has decided the step size is a half. So as you can see here, 0.5, 1.5, and as a result, T out is 21 by 1, because we're running from 0 to 10. Okay, if I change the pulse, so now I have a pulse of amplitude 1, I have a period of 1, that's the same, but I have now reduced the on time to 30% as opposed to 50%. Okay? So that's a pulse of 50%. Here's a pulse of 30%. I'm running from 0 to 10. I hit run. Look at the output vector this time. So we've gone from T out being 21 by 1 to T out being 101 by 1. So what's the step size? 0.1. Why do you think Simulink is choosing a step size of 0.1?
Irregular change.
Sorry, you did?
Irregular change in the graph.
What do you mean with that? Like, why isn't it choosing 0.5 here?
Because the graph isn't changing every 0.5. It's not regular, so it's 0.3, 0.7. Like it used to a pattern.
Yeah. So essentially what Simulink is doing is it's saying, right, we have a pulse here that changes 30% of 1, which is 0.3. So I want to make sure I capture every edge of that pulse. So I will automatically, because I've set the step size to automatic, I will automatically change the step size to capture that. In fact, if you try and set it to something else, it will give you an error saying, no, you need to set something that's a multiple of it. So in other words, the step size here is 0.1 and the pulse essentially is 0.3. So that's really showing you, again, behind the scenes what Simulink is trying to do in terms of choosing the fixed step size. And I'll finish off finally with this one. Here is the very same model, except this time I'm setting a variable step solver. Alright? So you can see it's variable step solver, ODE 45, and when you run the model, I mean it looks the identical, it looks the very same here, but as you can see the output vector is 65. Right? And if we look at the step size, this is what you get. Again, Simulink is deciding as the model proceeds what the step size should be, because now that it's variable step, it is designed to work within these tolerances here. Okay, that might be a bit heavy for Monday morning, I don't know if it is or not. But you do need to have some idea as to how these black boxes mysteriously turn out.